and good afternoon, everyone. My name is Xiao, a grade 2 master student from Research Group of Human Mobility Automation, Zhejiang University. The corresponding author, Daofei Li, is an associate professor of Institute of Power Machinery and Vehicular Engineering, Zhejiang University. He is also the leader of our research group. The co-author, Siyuan Lin, is a grade 3 master student who is our lab member. We are honored to present our research on lane departure risk assessment for hands-free driving functions. The outline of my talk is as follows. First, I will introduce the background and related work of our research. Advanced driver assistance systems, known as ADAS, has become widely used in passenger vehicles and achieved great success. Hands-free driving, which is an advanced form of level 2 automation, is also appealing in premium brand. But level 2 automation still needs human takeover when the system cannot handle the driving task. Therefore, a risk assessment module is needed to warn the driver to take over timely, which is extremely crucial both for safety and customer experience. Taking lane keeping scenario as an example, if the prediction of vehicle's future trajectory is out of current lane, then the system should warn the driver to take over. Therefore, one of the key parts in risk assessment is the ego vehicle trajectory prediction. Existing motion models used in trajectory prediction approaches can be mainly divided into two categories: physics-based motion models and maneuver-based motion models. Physics-based motion models feature model simplicity, high computing efficiency, and is easy for sortive validation, but the long-term prediction accuracy may not be that good. Maneuver-based motion models are mainly used in machine learning approaches, which can provide long-term prediction accuracy theoretically, but they need a large amount of training data with wide scenario coverage, and the models are complex and is difficult for sortive validation. Secondly, I will introduce our motivation and the framework of our proposed algorithm. For application, we think physics-based trajectory prediction is a better choice when considering the availability of vehicle states and the convenience of sortive validation. Besides, for automated vehicles such as hands-free function, the control actions of the vehicles are generated according to the tracking control law, which means the control law is known or can be learned. Therefore, we hope to extend the physics-based trajectory prediction utilizing the privileges of automated vehicle, that is, the known control law. The framework of our proposed algorithm is shown in the picture. First, an extended Kalman filter is used to filter the sensor noise and get the optimal estimations of vehicle's current states. Then a closed-loop vehicle dynamic model is used to better predict the future vehicle trajectory, considering the actual control law. The structure of the model is like this. Unlike existing approaches of trajectory prediction, besides sensing and planning modules, we also design a tracking control module for prediction. which can predict future control actions. The actual control laws can be learned or migrated from the control module. Given the vehicle states, control laws, and target speed or trajectory, this module can predict future longitudinal or lateral control action, like this. And the predicted control action will be input to the Kalman predictor with control, which we simplified as KPC. It can give a better estimation of vehicle states and predicted trajectory, considering the predicted control actions. And therefore, it forms a closed-loop vehicle dynamic model. Thirdly, I will give a brief introduction of vehicle modeling. Because we consider both longitudinal and lateral control, here we adopt 3 degrees of freedom single-track model, which considers the variation of longitudinal velocity based on the 2 degrees of freedom single-track model. Besides, taking lane keeping as an example, we also built the tracking arrow model, which can be derived from the single-track model if given the target trajectory. The arrows here is the lateral arrow and heading arrow. Firstly, I will introduce the implementation of Kalman predictor with control. About the car control law design, here the lateral control is designed as contained both feed-forward control and feedback control. The feed-forward steering angle is calculated by setting the lateral arrow in the arrow model to 0. And the feedback steering angle is designed using the LQR. For longitudinal control, a proportional integral controller is designed to track the target velocity. As I described before, first, in KPC, an EKF is an extended Kalman filter is used. Here we adopt the longitudinal velocity, lateral velocity, yaw rate, global coordinates of eagle vehicles, and yaw angle as the system state. Then, after getting the optimal estimations of the vehicle current states, we come to the control prediction. We can note that the arrows in the arrow model can be described as a function of the vehicle states, which is shown as the equation of x arrow. Therefore, based on the control law, we can predict the future control actions, like shown in the equation of U-pre. After we get the future control prediction, we come to the Kalman predictor, which can predict future vehicle states and afterwards generate the vehicle trajectory. In KPC, we take the vehicle states and the future control predictions as the inputs, and then we predict the vehicle states at the next time step with the state equation in the EKF. Then after we get the predicted vehicle states, it can go back to the control prediction, and given the target velocity and trajectory, it can calculate the control actions at the next time step and then go back to the state prediction. And this process will repeat again and again until reaching the prediction horizon. And the future trajectory of the vehicle can be generated by using the global coordinates of the ego vehicle in the predicted states. And therefore we can judge whether the vehicle will go off the current lane from the predicted trajectory. To validate our proposed vehicle trajectory prediction algorithms, we carry out a simulation of MATLAB Simulink and Cosine. We take the highway cornering as the simulation scenario to ensure the passengers feel comfortable. The vehicle should decelerate before entering the highway curve. So we designed the vehicle. So the vehicle in the simulation is designed to decelerate right after entering the highway curve and turn at constant velocity after deceleration. And the driving task of the simulation vehicle is lane keeping, which is tracking the lane center line. The benchmark algorithms we choose is CTRV, which is traditional physics-based motion models known as constant turning rate and velocity. Besides, for KPC, we also propose two kinds of KPC. The first one is KPCY, which is only considered the lateral control, which can be seen in this picture. Then is the KPCXY, which consider both longitudinal and lateral control. In this figure, it shows the prediction of all three algorithms within the prediction horizon of 2 seconds. We can see that at the prediction time of 1 second, the prediction of KPCY and CTRV shows an arrow in longitudinal direction. And in a prediction time of 2 seconds, we can see that the result of CTRV shows both large arrow in lateral and longitudinal direction, while the KPCY shows a large longitudinal arrow but relatively small lateral arrow. And for our proposed KPCXY, it can track and for our proposed algorithm KPCXY, the prediction results can fit the real trajectory of the vehicle well. This figure shows the root mean square error of the prediction results. As shown in figure A, we can see that considering longitudinal controller, KPCXY performs better than the other two algorithms. And as shown in figure B and figure C, we can see that both KPC algorithms predict more precisely than CTRV in lateral position and heading, because they consider the lateral control law. Besides, we can see that KPC-XY performs slightly better than KPC-Y because it considers the variation of longitudinal velocity, which provides a more accurate dynamic model. Finally, I will give a brief conclusion of our work. First, no uncontrolled law of automated vehicle is utilized to form a closed-loop vehicle dynamic model. Second, we propose Kalman predictor with control, which is known as KPC, considers the variation of control inputs in prediction, which can perform better in relatively complicated situations. Therefore, we think our proposed prediction algorithm can be promisingly applied in risk assessment for hands-free driving. Here I will thank for our sponsorship. This work is supported by Department of Science and Technology of Zhejiang and Ningbo Science and Technology Bureau. Thanks for their sponsorship. And thank you for your attention. If any question, please feel free to ask me. Thank you.